Thank you for the introduction. Okay, so today's topic will be the Kelvin Helmholtz instability. And I want to explain to you the relation to other plasma processes in Earth's plasma environment and its multi-scale character. So for this, I will give different introductions on the different topics. So let's see if this works. Okay, so my journey at the Institute, in 2019, I was an intern here for 2 months. And then in 2020, I did my master's thesis on the same topic that I will be talking about today. And in 2021, I started a PhD here at the Institute. So basically, today's seminar will be a summary of the last 5 years of research on this topic. And very basically, that's what we'll be talking about today. So one day after work, I went home during sunset, and I saw these very nice shapes on top of these clouds here. And this is the Kelvin Helmholtz instability. And these vortex structures are exactly today's topic. The only thing is, we're doing it in plasma, so we have magnetic fields, and therefore everything is much more complicated. Okay, so the contents of today will be a short introduction on plasma itself and on the magnetospheric MultiScale mission. Then we'll be talking about Earth's magnetosphere, which is kind of the laboratory that we have, and an introduction of the Kelvin Helmholtz instability itself. So we did not only use spacecraft data, but also quick simulations. So I will give you an introduction on these. And here the last point is then the outcome of my PhD, namely the multi-scale character of the KHI, which are the novel contributions from my side. And the summary and the outlook for future missions will then close the talk. Okay, so what is the plasma? You can think of it as the fourth state of matter, besides solid, liquid, and gas. And actually, it's the most abundant baryonic matter in the universe. So it's important to understand its relations. So it's an electrically conducting ionized gas. So what you have is charged particles, which are free. So here, for example, electrons and protons, or simply electrons and ions. And the ratio of the mass between ions and electrons is 1,836. And so having this large ratio of the mass of these two particle species introduces very different scales in your system. So the natural behavior of a charged particle in a magnetic field would be a gyro motion, meaning the particle would gyrate around the magnetic field at a certain frequency and radius. And so finding the frequency and radius for electrons and ions individually, they would be very different. So these sizes would give you a natural scale in the plasma system. And on the right-hand side, here's a very rough set of typical scales in the plasma around Earth. So in the plasma environment of Earth's magnetosphere. And so going from the bottom to the top, we have the electrons and the ions, and then kind of the system scales, which I will talk about later. And so what we relate here are scales of around 100 meters or 1 kilometer to 10 to the 6 kilometers. So we want to understand the whole system at all of these scales. And the tricky part is that they are interconnected. Yes. So what would happen to an ion or electron scales? For example, due to the very large mass, it would decouple from processes due to the very high inertia. So you would treat processes in the plasma at different scales differently. And the different approaches that you can use are either kinetic, ionic, or fluid, which means that you can, in a kinetic approach, treat the system as particles. So you have particles. And in a fluid approach, you would just have conducting fluids. This will be important later for the simulations. And the laboratory that we have is this here. So Earth's magnetospheric system. And there are a lot of things here that are not very relevant to this talk. So I will show you now the important regions that we'll be talking about. So the first point that is very important to understand the system is that the sun emits plasma. And this is called the solar wind. And this is transported towards the Earth here in this picture from the left-hand side. You can think of a flow coming in from the left here. And it dynamically varies in different parameters like density and magnetic field orientation, which will be important later in this talk. And the important part is that the Earth also has an intrinsic magnetic field, that is solar wind carrying a magnetic field, but they're disconnected from each other. And the frozen condition in plasma physics tells you that basically these two would not connect to each other. So they would repel. And what we have is Earth's magnetic field here as a kind of a dipole shape, and the sun, the solar wind coming in from the left. It would be deflected around this magnetic obstacle. So what you get is a very compressed day side region and a very stretched night side or magnetotail. And so basically the solar wind would not enter the system. However, for example, at the poles, we observe northern lights, which is a direct consequence of solar wind entrance and interaction with the atmosphere of the Earth. So there must be mechanisms how solar wind can be transported into the magnetosphere. This solar magnetosphere interaction and influence is why we're studying the Kelvin Helmholtz instability. And so how can we study this very large system? The MMS mission, or Magnetospheric MultiScale, depicted here on the right-hand side, consists of 4 identical spacecraft, which fly in a tetrahedron formation. And this guarantees for 3D observations. And you can therefore compute, for example, gradients. And it was designed to study the electron scales, so around 10 to the 1 kilometers, which is also the spacecraft separation. And if you think of the Earth's magnetospheric system as a very large one, this is an extremely small separation. And it was designed for the study of magnetic reconnection. And this concept is very simple to understand. You have 2 magnetic field lines in this sketch here that are oppositely directed. And the magnetic pressure here would be released into kinetic energy by breaking open these field lines, reconnecting them, and then kind of like a slingshot, having this outflow of particles. So magnetic connection is very important for the shape and general behavior of the magnetosphere. And it, as you see, depends on the orientation of magnetic field lines. So here we can look at 2 different scenarios at the magnetosphere. So on the left-hand side, you have, again, the Earth here is this dot. You have the magnetic field lines of the Earth exiting here at the South Pole. They are pointing upward, meaning northward, and they're coming again at the North Pole. And then from the left-hand side, you have again solar wind coming in. This blue line is being kind of the intrinsic magnetic field of the solar wind. And in this sketch, it would be directed downward, so southward. And this IMF means interplanetary magnetic field. And you can think if these 2 magnetic field lines come in contact, they can reconnect here in low latitudes or the base side region. If these magnetic fields connect to the tail, they would here reconnect again. And this would be a very rough sketch of how, for example, solar wind can enter the poles. Now, if we think of the other IMF configuration, northward, the solar wind will just be pointing upward, the same way as the Earth magnetic field. They will not reconnect here in this region, but they can reconnect with higher elements. Now, this is not so much important for this talk, but as you can see from this sketch alone, you have very different behavior of the magnetospheric system itself during these 2 IMF conditions. And this motivated our study on the Kelvin Helmholtz instability, because we're only studying this southward IMF case. Since, as I show you on the next slide, the Kelvin Helmholtz instability grows in this region here. So this would also be the one very much disturbed by reconnection, and therefore everything is much more complicated in this region, and we need to do a multi-scale study. So now we'll talk about the Kelvin Helmholtz instability itself. And so this instability is due to a velocity gradient. And this very simple sketch on the top here shows you two fluids, which are separated by an infinitely thin boundary layer. They have different flow velocity. And so the pressure gradient here would lead to indentations, which are wave-like. And these waves can grow into these vertical structures. And this is one mechanism how solar wind can very effectively be transported into the magnetosphere, which is why this has grown in importance in magnetospheric study. And favorable conditions for the KHI at the magnetosphere are at the magnetospheric flanks, which are these regions here. So the side wings of the magnetospheric system, or northward and southward IWF conditions. Because in this configuration, the magnetic field is perpendicular to the wave vector. And you can see this very easily in this sketch down here. We have the vortex structure here. The wave vector would be this white line, so in the horizontal direction, and the magnetic field points top, bottom. So these two would be perpendicular. And anything parallel to the wave vector would lead to a lower growth rate. And the important part from theory for the KHI is that we can compute this growth rate depending on the velocity gradient, which is here in term A. So here the u1 minus u2, so two velocities. And if this is very large, so the large velocity gradient, term A would be increasing. And then we have term B, the minus sign in between. And here you see that the wave vector and everything parallel to this wave vector would make the growth rate smaller. And so if we have northward and southward IMF, this is perpendicular, everything is zero, and so we have the perfect growth rate for the KHI. Now what this equation also tells you is that it does not matter if you have the northward and southward, because you can either have plus or minus, you will get the same result here. And so from theory, there should be perfectly no difference in northward and southward IMF for the KHI. However, in data, we see very strong differences. And that's exactly the topic of my PhD, understanding why during southward IMF, it's so hard to see these structures in data. And the reason is that you have different preconditions of the magnetopause, as I told you before. There's two different reconnection processes happening. They would influence the whole system differently. They have different conditions for the growth. Okay. So the topic of my PhD was to split this gap of observations. And therefore, we went into the MMS database and searched for KHI events during study. And if you remember before, I said that the spacecraft separation was very small, and we have very large scale waves. So why did we use MMS? Well, we wanted to do a multi-scale study. Usually spacecraft separations are much larger. We cannot really see electron scales or in part in the ion scales. But we wanted to see all these scales at the same time. And therefore we went through all the years of observations, and indeed we found one event on September 23rd, 2017. And here on the right-hand side, there was a nice gift from my first supervisor. During my internship 6 years ago, we wrote this sheet of paper, and here it says September 23, 2017. Nice. So that's basically following now for 6 years. And we also performed simulations for this event, not only Earth observations. And it's much easier to understand these concepts from pictures. First, we will understand everything from the PIC simulation, and as a final step, I can show you the spacecraft observations. Okay, so PIC simulation setup. The setup for these simulations is basically very easy, although they are very tough to do in reality. So what you do is you make this grid here in the simulation box, and you create your particles. If this is a kinetic simulation, you treat electrons and ions as particles. To make your life a bit easier, you don't treat individual particles, but you group them into these macroparticles. You can still have easily numbers of particles in your simulations of around 10 to the 12 or 10 to the 13. But if you compute everything in phase space and particles with very similar parameters, then most likely to be very similarly, and so you can compute it with macroparticles. And the concept behind the computation is the following: that you put in your particle, you advance them, and this would lead to different charges and electromagnetic field. They are computed on the grid points. The particles are in continuous phase space. And so this difference in the particle position, you then compute all the electromagnetic fields. And then again, you let these fields act on the particles. So again, they would be moving, you advance the particles, and so on. It's always a back and forth of these two. Now, since this looks very nice in this concept here, there are limitations. So first of all, since we treated as individual particles, they are very intensive computationally. So the box size and the resolution are often not bad, but very unrealistic. And also, one point that is strongly influencing them is the mass ratio. So this very large mass ratio of electrons and ions would lead to the fact that you would have an extremely large box size because the effects would act on different scales simultaneously. If you decrease the mass ratio a bit, and I told you it's almost 2000, in one run that we had, it was only 25, you can basically get rid of this large scale gap, and you can bring the scales closer to each other. This is very unrealistic, of course, but in most cases, you can still extract the physics out of your simulations, which I will show you actually on the next slide. So, now that we have a lot of information on the setups and MMS data and simulations and everything, I can now show you what we found during my PhD. So as I told you, we look at southward IMF conditions. We here perform a big simulation for the MMS event that I will show you only later. But it should be during the realistic observational parameters that we found in spacecraft data. And on the right-hand side, you can see a sketch of this simulated time steps, where from top to bottom, we have 4 different time steps in the simulation. We always have the low density plasma on the top and high density plasma on the bottom, which would be kind of the solar wind and the Earth's magnetosphere. And in between, we have the boundary layer of the magnetopause. And what you see from top to the bottom is that these waves are actually growing. So this is the Kelvin Helmholtz instability. And for later time steps, you have this kind of vertical shapes growing. But what is happening in the simulation is that they are not really rolling up as before, but what they're doing is these vortex arms are rolling perpendicular to the boundary. And this leads to very strongly distorted vortex shapes, as you see down here. This has nothing to do with any nice rolled up vortex structures. And the point is that here, a secondary plasma instability comes into play. And the first one that I can now show you is the Rayleigh-Taylor instability. And you probably all know it very well. Because if you just put ink into water, for example, you have 2 fluids of different density. They're accelerated against each other by gravity. And if you know you did this as a kid, maybe, then you see here these nice mushroom shapes growing in the fluids. Now, this is the fluid scale instability or system scale. So as I told you before, very large scale due to a density gradient. And this exactly led to this effect if the void structure is so strongly distorted. If you think that the Rayleigh-Taylor stability informs these vortices, and you would fly a spacecraft through these void structures here, you would not see a very regular shape, but you would see very irregular shapes here I will show you this later in the spacecraft data. So the second effect that we also identified is the lower Hadron drift instability. Now, for the radiator instability, since it's a case of thousands of kilometers, we cannot really measure it directly from MMS spacecraft data with a very small spacecraft separation. But for this one, the lower Hadron drift instability, we were able to also measure it directly. So as the name suggests, hybrid here tells you the scale is between the electron and ion scales. So this is perfect for MMS observations. And what it is seen up here in this first panel and also in the second one, you have these small scale perturbations along the edge here, along this boundary layer of the waves. And you see that a lot of plasma is transported from this high density region onto the low density side. Now, for Kelvin Helmholtz vortices, what you usually expect to have is very sharp boundaries. So if you would again have these, for example, spacecraft vortices here, you would see these structures and these perturbations. You would probably not think of Kelvin Helmholtz in the data. However, we found that they are very active in the shape of these vortices for southward hammer. And on the right-hand side, you see a 3D simulation of only one vortex structure for the same parameters as in the MMS event. And here I put a virtual spacecraft again. If you cross this region, you will see a lot of fluctuations in here. Here I plot the current density, but actually these fluctuations are especially seen in the electric field, in electrostatic instability. And yes, so a lot of particle transport due to this strong density gradient, and it again strongly destroys the vortex structure. And finally, we already heard about magnetic reconnection, but eventually in our event, we also found a connection. And the point that we want to study in an upcoming project is how these reconnections happen. So what we found is that at these small scale gradients here, the magnetic field can locally be very great and very strongly distorted, so you can have local magnetic reconnection, however, only at the electron scales. So what we have now is a very large scale Kelvin Helmholtz vortex, which is where the radiator instability acts at the fluid scales. Then we have the lower Hadron drift instability acting at the ion to electron scales, and then we found magnetic connection at the electron. So this very multi-scale character of the KHI can now also be seen in spacecraft data. So on the right-hand side, you see a lot of panels, which I will explain to you a lot of detail what we need from them. But so this MMS event was observed on September 23rd, 2017, and you see 1 hour of spacecraft data. And the first point that we can again look at is the radiator instability. We see it in the data. So as I told you, it distorts these vortex shapes, and it leads to this very irregular shape of the structures. And if you would fly a virtual spacecraft through here, you would have different lengths of crossing these segments. And so that's exactly what we see in the MMS data. On the top side here, I marked which are the individual vortices that we see. And these crossings will correspond to independent C, crossings from the low density to the high density values. In the simulation, this would correspond to something like here, crossing from the low density side to the high density side. And you see that the time span between these crossings is very different, very irregular. Yep. And also from different parameters that I have not the time to talk about here, we saw a kind of an indirect influence on the vortices. However, with this mission, we cannot measure it directly. So we would need a different spacecraft mission to hopefully see this at some point directly from data. But we see a lot of electric field fluctuations. And so they are plotted here in channel G. And the last panel here shows you the wave power of the electric field, where this black line, it gives you the frequency that is very typical for the lower hybrid drift waves. And so you see always at these crossings of the vortices, you have enhanced electric field, And down here you see the wave power is enhanced in this regime of this frequency. So with this, we were able to show the lower Harvard instability, not only from simulations, but also from data. This can be seen in more detail if we zoom into the vortex number 6 here. So that's a crossing of one of these vortices. You can see again from low density to high density side. On the right hand side, again, 3D simulation, and you go from low density to high density here. And in between, what you expect from this lower Harvard drift instability is mixing of plasmas. So what you expect is electron field fluctuations and intermediate density. And that's what you also see. The very extent of crossing the intermediate density values here. We have a lot of electric field fluctuations in this region. And we were therefore able to identify this as lower Harvard waves. Now, unfortunately, I don't really have the time to show you in detail why we identified the kinetic reconnection, but I can show you here that in this yellow shaded region here, we have a peak in the electric field, the electron velocity, and the current density. And from different analysis, we found out that this is reconnection at the electron scales. So with these observations and the simulations, we were able to relate all the scales, fluid, hybrid, and electron scales, for the KHI, and all of these scales differently influence the shape of the vortices and their evolution. Okay. So, in summary, we talked about the Kelvin Helmholtz instability, which is due to a velocity gradient. Here again is a sketch of the magnetospheric system. You have the solar wind coming in. Here you have Earth's magnetic field. And this solar wind is deflected around the magnetosphere. You have a very strong velocity gradient here, and therefore these shapes can form. Then the next point we identified was the radiator instability, which deforms the structures very strongly and is due to the strong density gradient. And then we found the lower Harvard drift instability, which leads to these fluctuations in this plasma transport locally at the boundaries. And in this region of fluctuating electric field, we found electron scale reconnection. This should be an upcoming project that we're now working on, where we want to understand in detail how these small scale reconnection is exactly formed. So the take-home message of this talk should be that the Kelvin Helmholtz stability during southward dynamic conditions is strongly connected to different plasma effects at different scales, and leading to a disturbed vortex evolution and also enhanced plasma transport, which is very important for these studies magnetosphere. And just as a final slide, because I think it's very interesting, 2 future missions that are currently not accepted yet, but hopefully they will be. One of them is the Plasma Observatory mission. And if you remember, the MMS spacecraft were 4 identical spacecraft. Here we have 7. On the top here, you see this very small red dot, which would be 1 spacecraft. Then you have this kind of triangle here. So you have the first tetrahedron at the electron scales, and then there would be a second one at the ion scales. So you could simultaneously study different scales with the same mission for the same effects. And for KHI studies, this would be extremely nice. And you have the Magnetospheric constellation mission. This would consist of 36 the spacecraft. And here's a sketch of it. They would be spread out through the whole magnetospheric system. Up here, you would actually see Kelvin Helmholtz waves. And if they transport plasma into the magnetosphere, with this mission, you can really trace the path of this plasma. And you can understand metascale effects and plasma transport. So if these future studies, together with high-resolution simulation studies, could focus on the KHI, it will be an exciting time to study it. So thank you very much.
So thank you very much, Kelvin. A wonderful talk. Yeah, I guess some questions.
Out if you want. Okay. In the slide where you show MMS and your Kelvin Helmholtz simulation next to each other, I was wondering what is the scale. So did you check the scale of the simulation? Does it match the scale of what MMS see? Or no, I think it was the MMS plot.
Which one exactly do you mean?
You have the MMS plots, like many of them.
Yes.
On the right side. Yeah, here.
Here, yes.
Before, yeah. So, because I assume the spacecraft are stationary in the plasma, right? They don't really move.
Yes, exactly. So these structures would cross the spacecraft.
And the size of this structure in the data, does it match the size in the simulation? Or is it, I guess, yes, but I'm just wondering.
Okay, now I know what you mean. So this is 1 hour of data. We have approximately 11 crossings, and you can estimate the size of these structures from their wave vector and the velocity. So approximately the wavelength of one of these waves would be 40,000 kilometers. In your box of the simulation, this is much, much smaller. So the mass ratio here is 25. You have a very small box, but eventually from these configurations, you can still extract a lot of information about it. It would not be possible from PIC to do such a study for different vortex structures in a realistic box size. What you also cannot really do in this simulation is put 4 spacecraft because the resolution is not good enough. However, for the electron scale theoretical connection, we performed simulations only at the electron scales, and there we put 4 spacecraft in the simulation. You can really see the differences. So here it's more like a qualitative comparison. It's not really quantitative, no. That's what I meant. So this different mass ratio gives you unrealistic scales, but you still see the effects. So you can still extract the physics out of it. Yeah.
Maybe a related question to this. You said the mass ratio is 25. Have you checked how the scaling behaves if you choose 50, for instance, or like going more to realistic value?
So for different runs, we use different mass ratios depending on the size that we have. So for example, for this one, this was a 3D run, but at even smaller scales, we were able to increase it a little bit. The points I didn't perform these simulations myself, like previous supervisor did, and it's mostly a trade-off between resolution and the time steps and the mass ratio. So in the end, we need some equilibrium that you can reach in the beginning of the simulation that is stable. And if you can achieve this, that's your parameters.
Excuse me. Thanks. Very good talk and very nice work, of course. The only thing that I don't know at the moment is if I look at the magnetopause during northward IMF, do I then see nicely wound up Kelvin Helmholtz vortices, or is this destroying of the vortices something that only happens with southward, or does it also happen with northward IMF?
That's a very good question. So for the northward cases, what you would usually expect is these very nicely rolled up shapes. The point is that this instability does not only depend on the global IMF configuration, but locally you can still have complicated magnetic field configurations, which could, for example, lead to reconnection at these boundaries. And then it doesn't really matter what IMF you have, it can immediately destroy the structure. So usually what this whole study should tell you is during southward IMF, it's much more irregular, but locally you can still have basically anything, no matter what IMF you have. Yeah.
I have a comment. At the beginning, as an appetizer, you show Kelvin Helmholtz waves in the atmosphere. And then you suddenly, which is of course obviously a remote observation, then you suddenly jump into plasma physics, And I think you could show also remote observations of Kelvin Helmholtz instability on the sun, for example. Yeah.
I have a question concerning magnetic field. How do you include it in your simulation? Is it a kind of the free factor, or you have magnetic field lines ends fixed, frozen in somewhere outside your box? Because in case your magnetic field lines are fixed, then it is an additional stabilizing factor, which would probably degrade your Kelvin Helmholtz instability development. If you let them free, then it will still take part in the momentum exchange between particles, but this stabilizing factor will go away. So I didn't get what are conditions in your particular simulation.
I don't really know what you now mean for the simulation if the magnetic field is fixed or not.
Yeah, you see in the global context, the magnetic dipole fields, they are rigidly fixed to the Earth, so they have certain elasticity. So if you simulate your intrinsic box, you have to get an assumption. So you should somehow reproduce this elasticity. So you fix the field lines, then they still can be deformed, but they do not move. It's one condition. If you let them to move, so they will be passively carried with the interchanging material. They still contribute to the momentum exchange between particles, because particles feel the magnetic field, but they will move together with the medium. So what is your condition?
So as you say, if they are fixed on the dipoles of the Earth, that, for example,
you are in the fixed box, so you do not need to involve this remote dipole, but inside your box, you should imply certain assumption for the field lines.
Yeah. So I don't want to say anything wrong, but what the setup maybe is, maybe I can show it someday. So the part that we would simulate is, for example, such a box around here.
Yes.
So we would only insert the magnetic field lines perpendicular to the simulation box.
And do you allow your field lines to freely move, just to displace with your medium, or they are somehow fixed? Zoltan wants to say something.
Yeah, the simulation.
I'm afraid it should be before this gradient increment expression which you provided. So the increment itself will contain this information, but also in the simulation you have to.
So in this out plane, it's periodic, so they should probably not be fixed, right? This wouldn't make any sense.
And it is a problem.
Maybe a short comment.
Rescue. Okay. The point is that in the data, we see Kelvin Helmholtz instability. The magnetic field, theoretically, and in simulations, can prevent the development of Kelvin Helmholtz instability because of geometry. Okay.
Yeah, if it is along the border, it's okay. If it is normal,
but he was trying to find a simulation box in which the Kelvin Helmholtz instability is excited and we see waves. Okay. The purpose of the simulation study was not to study different dampings or excitement of Kelvin Helmholtz instability, but to show when the Kelvin Helmholtz instability is occurs, then what is happening with these multi-scale things. But your question is, of course, right.
Well, this is a very general assumption. It can be made at the stage you switch to simulation.
So maybe this would be a nice discussion within the plasma physics group.
Maybe more comment on a question. Information about magnetospheric constellation mission is a little bit outdated in the Decadal survey from NASA. They have now announced a first priority mission, which is called LINX now. It has a reduced number of spacecraft, 20-ish like, but yeah, it's spherical constellation, new version, and they have actually the same time window approximately as the Plasma Observatory, and having the two missions all together would be a really golden age of the Plasma Observatory because well, links could provide us with some average profiles, for example, of the magnetic tail, plasma and magnetic field parameters. With the Plasma Observatory, we could do all the physics in 3D. This is one comment, and the second comment is the hybrid drift waves you showed on one of the slides, or hybrid drift waves. They are not solely the property of the Kelvin Helmholtz instability. They are property of a thin magnetopause. Whenever the magnetopause becomes has the thickness of on the order of the ion jar radius, we observe such low hybrid drift waves. And the main result from your study, I think, together with Takuma Nakamura, is that you found the way how to compress the magnetopause. So the Kelvin Helmholtz stability is able to do that work.
Yes,
and to provide us with the low hybrid drift waves and the diffusion, finally, reconnection.
Gradient.
Yes, the gradient is responsible.
Yeah.
The density gradient is responsible for the LHDR waves.
thank you.
Yeah, thanks for the nice talk. My question is it ever possible to observe these structures directly? For example, some kind of imaging in some wavelengths?
Yes, so for example, what Martin said, it was observed, for example, on the sun, or even
For the Earth, I mean, yeah.
on Earth.
Maybe a future mission?
Maybe I don't know. But as far as I know, there's no mission that would do it.
I mean, is it possible to do it at all?
Yeah.
Yeah, so is it possible to do it at all, and in which wavelengths, or what do you need, things like that? So
It is.
I mean, I have no idea.
okay, I also don't have any idea. So
Yeah.
thanks.
It's just like light, it doesn't emit much radiation, so that's.
I mean, wavelength is very hard because plasma, I don't think it emits anything there, but there is this X-ray from charge exchange. So SMILE, for example, if you want to observe the Bow-shock, the X-ray emitted by charge exchange from the solar wind to the neutral whatever. And of course, I mean, this question of resolution and so on, but I guess if there is in these instabilities, the structure emits X-rays because of some charge exchange of the solar wind getting inside the neutral, then maybe.
Yeah.
Thanks to Kevin for your very nice talk, but slightly answering your question. In Jupiter, the manifestation of such reconnection, you can see the fields are connected to the pole, so you can get a aurora induced from the Kelvin Helmholtz, which is in UV and X expand. Not the reconnection itself. And that also goes back to the question I wanted to ask. So very nice talk with the overview of your PhD. I don't know if it's part of your talk or part of the slides, the electron reconnection you showed at the end. I think that's a very localized reconnection. It doesn't contribute too much to the mass transport to the planet, I guess. Is it something you have looked at?
Yes, so we looked at this from simulation data because there we have the whole simulation box and we can much easier trace the mass transfer. And there we saw that this lower hybrid drift waves, they were very actively transporting plasma, but the reconnection didn't have any contribution that is comparable. And so also in the MMS data, we also estimated the diffusion coefficient for the LHDI. It showed similar values, a very strong transport. But for reconnection, we did a statistical survey where we checked all the current sheets that we found. However, only along the spacecraft trajectory, of course, not the whole vortex. And we only found one electron scale reconnection event with all of these boundary layers. So it looked like it doesn't really have an effect, which would be consistent with simulations, but from spacecraft data, it's a bit hard to say.
One suggestion, MMS has HPCA, which is a mass spectrometer. I don't know if you have the chance to have a look. If have you seen the data from that, or is it was an FBI? So they have oxygen. So if the footprint of the reconnection site is connected to the ionosphere, you might see outgoing oxygen, and that helps you maybe distinguish between local reconnection or it's connected to the ionosphere.
Okay.
Might be,
But this would be very large scale
yes,
connection, right?
yes. If it's not localized, then you might
Okay.
see that.
Okay.
Just a suggestion.
Thank you. Maybe a follow-up question from my side. You also did this on a statistical basis because you mentioned that you surveyed the data from 2015 on, and so now you just showed one event, the 23rd
We
September.
did a kind of statistical approach on these 11 crossings.
Okay. But
So there's the data again. Here it is. So as I showed you before, this number 6, we did this detailed study here. So down here you see this peak of the current density, which is one of these current sheets, and this one is reconnected. But inside the region, you see a lot of these flags. Which if you check all of these crossings and all of these current sheets, we did only see one reconnection event. That's what I meant. It's kind of a more or less statistical approach. Not statistical with 11 crossings, but it's still can expect some importance of it.
But is there a plan to extend it to more crossings, more days?
The problem is it's very tough to find these events in data. And you would need MMS currently to do this because so far we only see electron scale reconnection. So the upcoming project is to see why we don't see ion scale reconnection, if it's coupled to the scale of the LHBI itself, or if there's another mechanism that only allows for electron scale reconnection. And then the future would be, yes, to find more events with MMS data, and then, however, you would need to see the same mechanism. But in a different event, you would have a different density gradient, different IMF configuration, and you might maybe not have the same effect.
So that means on a visual basis. I'm asking because this immediately, what comes into my mind immediately is using machine learning, for example, to really identify such crosses.
Difficult.
And I think for the MMS data, we already do some sort of AI for the CPIC program, where you collect the data that is bounding. But what is, I think, much more interesting is current collaboration with my second examiner for the PhD, where we try to fingerprint different plasma processes using the parameter of the characteristic heating frequency. In there, you can see that for the KHI, no matter what IMF, and for reconnection and for mirror stability, we get very distinct results. This can help inspect large portions of data for characterizing if it's KHI or not. I think AI, I have no idea about it. But since different events are so extremely different, I don't know how to differentiate them. Yeah.
But good to hear that there are future plans and that you continue studying on this.
Yeah,
Very nice.
exactly.
So if there is one more question?
Online, yeah?
Yeah, it's just a nice summary. Thank you.
Oh, thanks.
All right. One last question. Sorry.
I guess these peak simulations are 2D simulation.
This one was a 3D.
Oh, really? Oh, I see.
The point was that we also did a 3D, but we did only see this LHDI in the 3D run because they need to move almost perfectly perpendicular to the magnetic field locally, and in the 2D it was suppressed. So it's a very three-dimensional effect actually. That was also the reason why we only have one vortex, because in 3D it's so intensive to compute things.